So using equation 2, 3 and 4 in equation 1, I would get the left hand side is 0, followed by I have the dou by dou y of mu t. Mu t, eddy viscosity is what we found this as u star kappa y, right? U star kappa y, eddy viscosity, by sigma epsilon dou by dou y of epsilon itself, which is u star cube by kappa y. Okay, the diffusion part is done, and the production, which is plus c epsilon 1 epsilon by k. Epsilon is again u star cube by kappa y, epsilon by k, so it's 1 over k is c mu raised to minus half u star square, and then pk, which is u star cube by kappa y. And finally the destruction rate of epsilon, which is minus c epsilon 2 epsilon square by k, which is u star cube by kappa y whole square by k here, by k, which is c mu raised to minus half u star square. So I substituted all the scales here. So if I go ahead and differentiate this, before that you should know that u star is a wall friction velocity. It has no y dependence. Okay, it's a constant for a given flow problem here, right? Or it will be in a developing boundary layer, it will be a function of x. As you walk along x, the u star can change, but it will have no y dependency. It is defined for all the wall, right? It is coming from wall shear stress. So u star has no y dependence. Kappa is one common constant, no y dependence. Sigma epsilon has no y dependence, right? So should know here that u star, kappa and sigma epsilon are independent of y. So therefore I can write this as 0 equal to, this thing comes out here, which is u star kappa by sigma epsilon, u star raised to 4 actually, right? Kappa y will go away, oh sorry, kappa will go away here, the other kappa comes in here, and then I get dou by dou y of y dou by dou y of 1 over y. This is going away. Let me know if there is any mistake. Plus I have this term, which is any term that goes away, u star square is there, kappa y square it becomes, so I get c epsilon 1 c mu raised to half u star square, and this goes away, giving to u star raised to 4 by kappa y whole square minus is it any mistake I have done? No, this is fine. So c epsilon 2, here I get C epsilon C mu raised to half, and then U star, again here this will become 4 by kappa y square. Okay, so if I go ahead and differentiate this, so basically U star 4 goes away here continuously, U star 4, U star 4, U star raised to 4 goes away, and so I have 1 over sigma epsilon, differentiating this, this is minus y by y square, that is 1 over y, plus C epsilon 1 C mu or square root of C mu over kappa square y square minus C epsilon 2 square root of C mu by kappa square y square. Essentially it has come to both. So now the difference is only in the C epsilon 1, C epsilon 2, right? If these two values become same, C epsilon 1 is equal to C epsilon 2, that means your production rate of epsilon and destruction rate of epsilon is becoming same. Okay, so now you have on the other side, so this goes away here, y and this minus 1 by y, so this becomes essentially plus, so I get 1 by sigma epsilon y square plus C epsilon 1 by kappa square y square minus C epsilon 2 by kappa square y square. So y square goes away. So this becomes essentially, so I need to find out the value for C epsilon 1 here. Sigma epsilon I know the value from computer optimization, I have the value. C mu I know, right? C epsilon 2 I know kappa. So I can substitute all these constants to get the value for C epsilon 1, correct? So C epsilon 1 essentially becomes, so C epsilon 1 square root of C mu by kappa square will be equal to C epsilon 2 square root of C mu by kappa square minus 1 by sigma, or I can say C epsilon 1 is equal to C epsilon 2 minus 1 by sigma epsilon times kappa square by square root of C mu. Sorry. So I have the values for all the constants here. C epsilon 2 is known, so I can substitute this as what was the C epsilon 2? 1.92 we use, right? 1.92 minus 1 by sigma epsilon was 1.3, kappa square 0.41 square by square root of 0.09, right? So if you do all this, I get C epsilon 1 equal to 1.44, sorry. Okay, so the 5 model constants are now given in the equation. It is C mu equal to 0.09. This is in the standard k-epsilon model. Standard k-epsilon model. and then sigma k equal to 1, sigma epsilon is 1.3, and then C epsilon 1 is 1.44 and C epsilon 2 is 1.92. So these are the constants that are used in standard k-epsilon model. Okay, so the reference for this standard k-epsilon model is, if you want to go ahead and look at the original article where they have published, the one who have come up with this model, Launder and Sharma, 1974. So this article you can download and look at it. This one?
Yes. Is it the similar reasoning?
Similar reasoning, yes. So they are using this 1.44 for accommodating the other types of flows. This is accommodating other class of turbulent flows, especially the free shear turbulent flows. So one can go ahead and get these constants for different types of flows. You need to make different assumptions, different considerations, right? We have omitted certain, we looked at log law, we looked at certain types of flows. You can, of course, there is no golden rule here. You can go ahead and look at a different flow and see whether this model constants work. Okay, but I think they have already looked through that by making this 1.92 and 1.44. Yes, so if I use the same value, what do you get? What was the value that was coming out to be here? 1.489. Okay. So now if you see this 1.489 and 1.92, okay, this is C epsilon 1 is much closer to what they have found here. But if you go back and see the formula for the production rate of epsilon and destruction rate, the main difference that you get here is actually this value here. Here you see, upon introducing scales, this particular term is now exactly the same. So what you choose for C epsilon 1, C epsilon 2 decides how much production rate of epsilon is there. So you need to see this is a coupled system. So production rate of epsilon is large, means your more epsilon is being produced. More epsilon being produced means turbulence kinetic energy is drained away from the system, right? More epsilon means less K, and that will stabilize. So in some flows, the turbulence kinetic energy can outgrow or become very large, destabilizing your entire calculation. So a higher epsilon leads to a lower K, stabilizing the flow. But this a lower K also means that you have lower turbulence. For example, if you are looking into a turbulent jet, and the jet will grow as we see, any shear layer or a boundary layer grows based on the turbulence intensity. So turbulence intensity can be thought of as square root of K, a turbulence velocity, right? So that means K is higher means the jet will grow wider. So you can actually manipulate here, right? That's why this entire RANS model is purely statistical. You can decide the size of the jet purely by micromanaging all these parameters here. You can get a wide jet or a narrow jet just by changing all the model constants or working with a different type of a k-epsilon model. So your excessively it is user dependent. You have a say in how the flow should look like, rather than the flow is telling you what it should be. For that we have to go to eddy resolved methods where the flow itself decides what it should be. Okay, so RANS approach is like this. So I am just explaining to you what it is all about, right? So now we can look at another, we can quickly go back and see, let's say, no, I would like to tell about another type of k-epsilon model, which is also very popular. I will not go ahead and derive this because then the entire course will be just k-epsilon models. Okay, so I would like to move on to other types, but there is something called RNG k-epsilon model, which is also popular. So I'll just quickly give what is the main difference between not in the derivation. Derivation is very different. But at the end, when you look at standard k-epsilon model and RNG k-epsilon model, what is the main difference? That I would like to give you and tell you what is the new thing that they have done. Let's quickly look at this. What is called RNG k-epsilon model. This RNG stands for renormalization group. It's a group. So there is a reference for this. It is Yakut et al. 1992. So it's almost like 20 years later this model has come. Standard k-epsilon is 1972, 1974. About 2 decades later this has come. So the primary difference in RNG k-epsilon is, of course, the model constants are different, and one model constant is actually calculated. Okay, so the C mu value takes 0.085 here, not 0.09, and sigma k takes 1.0, same as before. Sigma epsilon takes 0.719 and C epsilon 2 takes 1.68 here. But the interesting thing in this model is C epsilon 1, that is the production rate of the epsilon. That is, there is a new influence here because C epsilon 1 is calculated. Okay, so the most interesting part here is that interesting feature is C epsilon 1 is calculated. So it is dynamic. This value is not constant, right? In a given flow, this value keeps changing at every point or in time. So C epsilon 1 is calculated, and the way they calculate is, I call it C epsilon 1 star. If you actually go and look into this model, they may call it a different name, a C beta or a C gamma, whatever. They would have called it differently, but for you it's easier to understand if I am using the same terms, C epsilon 1, C epsilon 2. So I am calling it C epsilon 1 star. This formula goes like this: 1.42 minus eta 1 minus eta by eta 0 divided by 1 plus beta eta cube. So this is the formula they are using. So what is special here is that this eta, they are looking into, so far we have looked into only turbulent time scale, k by epsilon. There is also a flow time scale that you can use the strain rate, right? Dou u dou y will give you a flow time scale. So they want to use the computation between a flow time scale and a turbulent time scale and introduce that into the flow. So that's a very interesting feature here. Okay, this does not mean that RNG k-epsilon model is better than standard k-epsilon in all the flows. There are flows where standard k-epsilon is good. There are flows where RNG k-epsilon is good. You have to figure it out which one is working good for you. Okay. So here eta is the ratio of turbulent time scale over the flow time scale, or I would say mean strain time scale. So it's essentially, the formula goes like k by epsilon divided by 1 over s. So this s is, or I can rewrite this as s k by epsilon, where s is nothing but square root of 2 Sij over bar Sij over bar. Okay, so you are making use of this, so that means you need to dynamically calculate in your flow, and other model constants I will give it to you. So this is eta 0 value is 4.38 and then beta is 0.012. So eta is being computed. on the go when simulation is running, and they are looking into the computation between these two scales. One can also introduce some other scale. So since turbulence is a multi-scale problem, if you feel the k by epsilon or any other turbulent scale that you have is not good enough, you can look at that. And many popular models, they have already looked into this, including this. Okay, but the derivation takes a very different form. I can share the article for you, or you can download this yourself and you can see. Okay, so this is one other form of a k-epsilon model. There is one more called a realizable k-epsilon model. For that, that is actually, instead of going into just a realizable k-epsilon, I would like to introduce what is realizability. There must be something unrealizable here in the model. So I will first discuss what is unrealizable, and then the fix, which is realizability constraint, that you can easily apply to any of your existing model rather than implementing a new model. There is actually a realizable k-epsilon model, but for any of your eddy viscosity model, it is a good idea to just implement the realizability constraint so that it becomes realizable. Okay, so that form I will discuss when we go to realizable constraint, realizability constraints. I can quickly go and look at a one equation model here before proceeding. I told you in the beginning, if you do a two equation model, it's very easy to do a one equation model. So we'll quickly go back and see. It's not very popular. There are some models which can be popular for a different reason. So I'll quickly go to what is called a one equation eddy viscosity model. So here there are different models, Pallart, Almaraz and so on. I will not go into that one. I will discuss one which is called Prandtl's model. Okay, so this model, the K model equation is same. No change in that. Dou K by dou T plus uj bar dou K by dou xj equal to dou by dou xj of nu plus nu T by sigma K dou K by dou xj plus the production rate term that is modeled, which is your Boussinesq 2 nu T Si j minus 2/3 K delta Ij and your strain rate term minus epsilon. So up to this, it's the same part as any other k epsilon model, but here for epsilon we actually have a model transport equation. In one equation, obviously there is no transport equation for epsilon, right? Here we simply take an algebraic form using dimensional arguments again. Okay, so no transport equation for epsilon is used here. No transport equation for epsilon is used. Instead, epsilon simply comes out to be the epsilon model term here, this one, simply dimensional arguments, which is C mu K raised to 3/2 over one turbulent length scale. Okay, dimensional arguments here. So the question or the main drawback of this model is, what is L? You need a turbulent length scale that you have to give, and so the question is, what is L? So this is user dependent. You can plug in whatever value and get whatever solution you want, which is not a very good idea. Okay, so that is the main drawback here, the main disadvantage, since it's user dependent. So eddy viscosity is of course calculated here. We have eddy viscosity calculated same way as C mu K square by epsilon. epsilon, of course, I have given you the formula, and the model constants are sigma k is 1 again, and what else? I have sigma k eddy viscosity. That's it. Epsilon is given, and the C mu value, of course, the C mu value here ranges from 0.07 to 0.09, depending on if you are doing a wall bounded flow to a free shear flow. There slightly changes in the value occurs, and the turbulent length scale, as I said, is the biggest problem here, user defined, and that means you can see here, if you want, if you define a large L here, okay, let's say you define, let's say this is a pipe flow, you put turbulent length scale as the length of the diameter of your pipe or something. That's not a turbulent length scale, but let's say that is what you are giving. A very large L will make epsilon becoming small. So a small epsilon leads to higher turbulence kinetic energy. So you can actually again control turbulence kinetic energy in this, and turbulence is actually taking away the momentum from the flow. So that means you can control your flow essentially by controlling the length scale, which is not a good idea, and that is the main disadvantage here, a user defined turbulent length scale. Okay, so a large L, okay, leads to small epsilon, which further leads to large K value, and vice versa. You can just interchange to get whatever you want, which is not a good idea. Okay, any questions you have, I can take it up. So one equation, two equations, we have looked mainly one particular equation, k epsilon model.